Um, this session we wanted to mix it up a bit also with this session and transit analytics applications from the field. So as I mentioned in the previous session, I've been monitoring the use of data, especially automated data in transit for a very long time. In fact, managed to early report in 1991 when I was at the Canadian Urban Transit Association, and been monitoring since then. Very slow progress until recent years when the availability of data, the technology that made that data available, new techniques, new methodologies, and a growing understanding of how powerful data was started to grow. And first on sort of the academic side with a series of workshops, transit data, that I was involved in, but most of the other people were academics. And then in 2020, Amer and I co-organized the Transit Data 2020 International Symposium. And I've been watching a small number of agencies that are really on the forefront of the use of data and the development of transit analytics. And so we've invited two of those real leaders, Metro Transit Minneapolis and WMATA in Washington, DC. And I've known both Eric Lind and Catherine Vanderwerk for some time, and they were both involved in the Transit Data 2020 Symposium. So I asked them to join us today to present a bit of what they wanted to present, a potpourri of different applications. I've seen bits and pieces of these, and they're very cool, and I thought it would be fun to share them with the participants in the workshop. I will let each of them introduce themselves. The first one is Eric Lind. He's Manager of Research and Analytics at Metro Transit, which is in the Minneapolis, St. Paul area. So Eric, can you share, and I will go away.
Sounds good. Thanks, Brendan. How's that presentation looking?
Looks good.
Thanks. Thanks all for having me. This has been really exciting. I really enjoyed this morning. So really appreciate the invitation to try to talk a little bit about how we are applying some of these ideas about analytics on all the data in transit in practice at an agency, sort of medium size. Let me advance here. So context in Minneapolis, St. Paul, just your neighbors to the southwest somewhat. Actually, I think we might even be north of Toronto. We operate a fleet of buses in which we do local bus, commuter express bus, and some BRT. We have 2 light rail lines. We have 1 commuter heavy rail line. And just for context, we were averaging between 80 and 85 million trips annually up until the onset of the pandemic. And now we are in the 36 million range, and probably we'll get back there again this year. I'll have more about ridership and how we're forecasting it later on. So just to set the stage a little bit about how we're doing data science at Metro Transit, and this is a pretty broad term, data science, as you know, but it encompasses data management and engineering, and also analysis and visualization and documentation and many other things. So all the many things that go into making data useful. But just as a little vignette of the general types of things we do. So Brendan mentioned we're focused a lot on automated data. We get automated data from lots of different systems. For instance, from our bus system, we have a vendor database, because ultimately all those messages are being produced to enable the real-time management software in the CAD AVL system to be able to let the supervisors in the control center understand and manage what's going on out there. But those data turn out to be super useful for lots of other things. And so it's been our practice to extract, transform, load in the phrase of the practice, an ETL database, where we can basically take those raw messages and kind of distill them into something that's more useful and set up a dashboard against it. For instance, something like on-time performance, where we have processes producing these data, and so we can now always know what was the average on-time performance for some part of the system or route, whatever it might be. What we started doing in our group, which is called Strategic Initiatives inside Metro Transit. So we're sort of a small, I don't know, agency consultant shop, right, within Metro Transit. We do lots of different things for lots of different people in the business. But it so happens that we were an R shop based on the people that, you know, kind of came in various pathways into working for Metro Transit. A lot of us were coders in our statistical software because of our academic histories. And so what we've been doing is building on that ability to do even more things with the data. And what I'm going to show today are just some examples of how we do that. We usually work in a shared coding environment using GitHub, and we can produce lots of different types of things, interactive applications like web applications, you know, standard reports, lots of analysis, whatever it might be. So that's kind of the general framework. We work on lots of different types of data, and it was actually very nice to be able to look at your agenda today and say, hey, you know what, we do all these things. So I'm going to show you a few vignettes of planning and scheduling analytics, operations performance analytics, some policy and equity work. One thing I'm leaving out that our group does do some of as well is more survey work and other qualitative research about travel behavior, rider experiences, kind of that adding in the person element to the data is all part of the research and analytics group that I work with. Okay, so first, just some examples of analytics that we're doing to improve planning and scheduling. I'm going to focus on deadheads, and it was nice to see this was also of interest earlier this morning, thinking about putting deadheads into a scheduling framework when you're trying to optimize bus assignment, which of course we're doing all the time. So one thing we can do is look at how the deadheads that we have are operating now. And there's a couple different components to this. Deadheads are not planned in a turn-by-turn way at Metro Transit. So the bus operator knows where they finish their trip, and they know where they have to start their next trip. They know how much time they have, but they are not giving directions. So sometimes there's a lot of variability in how they choose to move from point to point. And of course, they have the freedom to do that. The question we had is, how can we estimate the distance and assign it correctly, and also understand where that distance isn't working well for our detection software? Basically, when our buses are traveling between trips on a deadhead, we don't detect them as being in the right place until they arrive at the next terminal. And in order to do that, it has to travel a certain distance in the CAD-AVL system. So basically what we're doing is taking data from the last trip to the next trip and estimating how far, in this case in feet, because that's our good old English system, how far the bus has traveled between those 2 points. And you see this range of dots here. So this is for this particular deadhead between Haywood Garage and the forget what GTLO is, sorry, the next load point. You can see the variability that happens in each trip. So, you know, 1,500 feet, so it's not a terrible distance, quarter mile or so, but there's still variation from time to time. And the problem that this application that we put together is trying to solve for the person managing the CAD-AVL system is, what distance should I be setting in order to capture basically the most of this variation? So they can look at these one by one, they can look at them in bulk, it can download all the data, but this is an example of just putting data in a useful format by pulling stuff out of that CAD-AVL system and then feeding it back in terms of optimizing a particular parameter. The other thing we do is actually improve the data. So one thing that our system has trouble with is actually these detections, especially in urban areas. As you know, like GPS tends to wander in, you know, what they call an urban canyon. If there's a lot of tall buildings around, if the bus is making small movements, which of course they do around a terminal. So on the right, you see just an example of a bus, and each little point is a GPS ping, and you can see how it enters the zone of this terminal and how it exits again. And we can kind of timestamp, location stamp the first time it was in the zone, the last time it was in the zone, call that the layover, right? On the left, you see this two-colored histogram The blue color represent what the CAT-AVL system thought happened, okay? So this is a distribution of layover times. And so you see this big spike on the left at 0. Well, that's because it didn't really capture any layover time at all because there was a detection issue. But when we synthesize this by doing this GPS overlay against the zone, you can see there's actually kind of 2 distributions of layover time. There's one that's centered around 10 to 15 minutes, which is probably the target. There's one centered around 5, which is maybe shorter than we'd like, but still doable. And you can see that the average in the CAT-AVL system below there was about 6 minutes, but that was combining lots and lots of zeros with lots and lots of 10 to 12s. So it's not really representative when we talk about how is this layover scheduled. Is this scheduled well? It looks like it's scheduled okay. There might be some interest in those 5-minute layovers, but if we looked at that CAT-AVL data on its own, you would think that there was a pretty severe problem here. So we're not only analyzing the data, but we take this data, we synthesize new records and basically put them back in on our reporting system. So we have an improved data set. The other thing we're doing is trying to predict travel times for deadheads that we haven't operated yet. So as was discussed earlier, one of the things these schedule softwares will do is try to optimize the schedule as a whole. So you've got all these different trips. How do you minimize the number of buses you need to operate those trips? You do that by deadheads. And the thing about deadheads, again, that we don't plan them turn by turn, and we don't operate all possible deadheads. So when we look at this dot map here, a subset of our terminals, we don't have observations from the bus about how long it takes to get from one to the other in all cases. But that's what we want in order to optimize the bus scheduling software, right? So instead what we're doing is taking this approach where we're taking the endpoints, we're running them through a trip planner, open trip planner in this case, to create a travel time matrix based on general purpose traffic. As a side note, we had looked at using some of these big data solutions, but the problem we had in our case is when we feed these into sort of those big data tools, there are just so few trips happening between any individual pair of points. Our bus terminals are not necessarily high volume auto traffic places, that we really couldn't get reliable observations for all of them. So we kind of abandoned that approach and went to this trip planner approach. So we're running them through a trip planner, and then we're modeling the bus travel time against the trip planner in sort of a hierarchical model, but basically using, so there's a travel time scalar for each time of day, basically, right? Where in the PM peak, you might add more time than you would in the morning or at midday, but in general, they all should be related to the amount of travel time there is at the auto level. And then we're going to predict, using this model, the unobserved deadhead. So it's kind of a classic train and then predict approach, just using kind of a regular hierarchical linear model. But we can get these nice outputs of variability. And if we want to use like the 85th percentile to account for delays, we can do that and understand, okay, if we put this into the scheduling software, now it might take advantage of some link that we've never thought of or never operated before, because now it has a travel time to base it on. Okay. So another set of projects involve operations analytics. So in our case, we work a lot with the bus data, but I was excited to see that sort of dynamic bus lanes and transit signal interaction presentation this morning, because we are doing a lot with understanding how transit signal priority improves our performance. So we built another tool. So this is another RShiny tool. It's just an interactive website, but in this case, it allows a spatial query. A user comes in and they'll draw a box, and you can put in these cute little cartoon bus stops and signals so you know what you're looking at. You choose a route and a couple date ranges from there over there on the left. And it will pull the data for all the trips it observed. And by the data, I mean the AVL. So our buses are reporting their locations every 8 to 10 seconds. So we have very good resolution where in any reasonably sized segment of its path, you'll be able to identify its travel time through that path, through this box. And so that's what we're getting here. And the question we want to ask in this before and after is, okay, we have a before when transit signal priority was not in operation yet. We have an after when we think it was working well. How did that impact our progression through this particular intersection, which happens to be at a junction point with a big highway entrance. So there's often a lot of turning traffic, for instance. So as an output of that, what we get is some nice distributions where we can understand a few things about the, I'm just gonna turn my laser pointer here, understand a few things about the progression. Okay, so first of all, in orange, we've got a before time period, and in blue, we've got an after. And for the sake of argument, we've identified these periods as being relatively free of other construction or detours or weather or things like that. So we're just going to say these are good before and after comparisons. What you can see is we have graphed the mean travel time through this intersection, but you can probably tell by looking at that doesn't really capture what's going on. So when you look at all the data, which is the data down here in these little dots, you can see how the structure of the progression really changed. And in orange, there's this kind of smear between 6 and 12 seconds to get through that box. But in the blue, the after period, it's been really tightly organized, essentially to 8 to 9 seconds. And what this is turning this random arrival with respect to the signal being green into more tightly clustered arrivals when the signal is green. Because now the bus is progressing through that signal and not having to stop and wait like it did occasionally when it arrived in the orange period. You can also see these kind of like harmonic signals of when that signal and other signals might have been red or green, and you see this kind of predictable binning of progression, which is interesting to think about. But overall, the main message would be there's a lot more kind of free flow through this intersection and a lot fewer cases where there's a significant delay, so a 30-second delay. Now up here, we've got a checkbox which I've used to eliminate times when the bus actually stopped and served passengers. So the signal priority works best when actually the bus doesn't stop to serve passengers. It's just kind of flowing through because it can optimize the signaling a little better. But in some cases, we do have, oops, that was the wrong way. In some cases, we do have passengers to serve. And so when you think about, okay, what is TSP doing for our progression? It was lowering the travel time by a few seconds on average, but really moving more of them to that sub 10-second period. When we look at what happens when it has to stop and serve passengers, you can find out that, of course, this is where the real impact is. So if you look at the case where it doesn't open, the vast majority of times the bus is getting through in under 20 seconds. When you look at a passenger activity record, it's taking more like a minute, which makes sense. But it's also important to consider when you're talking about scheduling improvements, reliability, travel time. We have a lot of focus on how can we get the technology to work better. And really, one of the things we have to understand is that, as was discussed earlier this morning, this stochastic element of whether passengers are going to show up or not is actually way more impactful. So adding in that uncertainty about passenger activity can really help us understand our expected travel time, irrespective of whether there's nifty technology at the signal. And so that's something that I appreciated about the talks this morning as well. Okay, I know later this afternoon we're going to hear about some other work on equity metrics. Just want to pause and indicate that we have had a statement of equity in our agency and our regional planning body for quite a while, but I would say it was taken much more seriously after what happened in May 2020 with the police murder of George Floyd. So that happened at 38th in Chicago and Minneapolis. Obviously a worldwide news event and everything that followed, but this is taken only like one day after that event. And it's showing to me like the importance of Metro Transit in this community, because this bus stop was turned into a shrine, which it pretty much still is today, on Route 5, which is our single busiest local bus line, and shows how the community incorporated Metro Transit. And our job is to reciprocate that, right? Our job is to make sure that we understand what the community needs and that we're serving people equitably. So we did have a lot of internal motivation, internal charge from our general manager to develop new metrics about how well we were doing in equity. So just briefly to go through kind of how we're doing that, we're taking an approach of opportunity rather than who's using our system. So in other words, who is able to do what on board transit, not necessarily who is already doing it, okay? So we're using our US Census data, the American Community Survey, which helps identify for a certain geography and block groups, the proportion of people that are white, the proportion of people that identify as Black, Indigenous, people of color, which we have abbreviated BIPOC here. And so what we're doing is creating walk sheds for each bus stop in our system. And that's what this blue quadrant represents there. So that's how far a person could walk starting at that bus stop in all directions in 10 minutes. And that kind of diamond shape represents the fact that you're walking along a perpendicular street grid. So kind of the farther you get away, you have to make more turns and you don't quite go as far, right? So we've taken those walk sheds and we're overlapping them with our census areas and using proportional methods to try to identify for that walk shed, for that bus stop, who lives nearby and therefore can access that service. So once we establish for each walk shed kind of the proportion of people, we can use those to then attribute anything else about the service to that bus stop. So you'll see some examples of metrics. They all come back to, okay, if I boarded at that bus stop, what would I experience? So we can look at just the number of trips available. The figures that follow are organized the same way, where you've got some variable we're measuring on the vertical axis, and then each of the identified race ethnicity groups on the horizontal axis, and the ones that are basically used enough, like basically responded enough in our region, are Black, Native American, Asian, multiple races identified, Hispanic, and white alone. And then there are others. So we look at those proportional population composition at each bus stop and then average across the whole system. The average is represented by this horizontal line. That's sort of the regional average. So on average, if you live near a bus stop, you have 53 trips serving that bus stop on a day. For those that are Black or Native American, American Indian, they actually have higher proportion of access. So the average resident who identifies as Black basically has 58 instead of 53. So that's the idea behind these metrics, that we're disaggregating by race the opportunities that are available. We can do the same things with accessibility to jobs. So for each bus stop, we go ahead and calculate how many jobs someone can reach in 45 minutes at noon or at 8 a.m. And from this, we can also see that not only does the amount of service, but what you can do with it really benefit Black and Native American populations proportionally more. And this has to do with essentially the geography and really, honestly, historical, segregation patterns that we happen to serve certain neighborhoods really well with transit. Something that's more interesting is kind of looking at on-time performance. So when we see, okay, there are a lot of trips, how well are we meeting the schedule? Overall, we have an 85% on-time performance, which is not great given our sort of generous metric for that. But we have observed more variation in terms of who gets what type of on-time performance. And partially that has to do with the fact that we've had a lot of trouble filling our schedule. So unfortunately, we've had to cut trips from the schedule on a short-term ad hoc basis because we don't have enough drivers for that schedule that day. And this has been a real problem. It was a real problem in 2021. We've reduced service again. We're going to reduce service again in August a little bit. It's not great. It's not great. And the impacts are disproportionately falling on historically marginalized populations. So if you're a Black or Native American person living near a bus stop, you're more likely to have experienced a cut trip in the last scheduled period in 2021. So we have to identify these pieces of equity to understand, how we can do better. This is certainly not the only, dimension of equity if you're thinking about transportation, because all of this is in the background of, our region is primarily built for autos. Auto access is very, differential and limited. So it's not the full story, but for us, it's what we can control. We can control how these aspects of service are being put out there and if they're being put out there equitably. Okay, then the last bit I want to share, and I'm running out of time, is ridership forecasting. This is something that we have a lot of questions coming our way about, and just wanted to give a little background on our methods here. So every transit agency has essentially the same sort of data when it comes to ridership. It's time series data by month, by week, by day, whatever it might be. There are a lot of tools out there, statistical tools for evaluating time series, and we've adopted some of them. One of them is called decomposition, STL decomposition, but basically you can take out of that time series different mathematical pieces, the seasonality component, a long-term trend, smoother, and then some leftover random variation. And so when we do this with all of our time series, we can get information about, for instance, this route is particularly busy in February and in October, okay, and less busy all summer long. This route happens to be associated with a university campus. You can also see there's this long-term trend where, demand changed radically at one point, service changes were made, it kind of came back and so forth. So all we do for our predictions is essentially take these decomposition outputs and then add up, going forward, the trend and the seasonality. We kind of leave out the random variation, or we know it's implied. So if we add in the trend and the seasonality, along with what our expected error is for those predictions, we can kind of get a pretty good idea of what's going to happen. Now, before COVID, this worked really well. We'd really get bang on predictions, and our finance department was slowly coming around to using these predictions instead of their somewhat older spreadsheet models. But then COVID comes along, what do we do? I mean, because the trend is essentially no longer valid, right? We have something that looks like this with a giant cliff. How do we take, that and project it forward? Well, our answer to that and dealing with this uncertainty is to do scenarios as much as possible. And so we're doing the same modeling approach, except now we're using essentially like a tuning variable to say how close is the observed ridership impact going to be to pre-COVID. And so we can kind of switch that around, and we're not modeling people's behavior, but we're naming these things as if we are. And that helps with understanding at the executive level, let's say. So, for instance, we can have a pessimistic model that says basically it's going to be the same as 2021. We can tune it a little higher to say it's going to be more regular travel by the end of 2022. We can have an optimistic model that says, yeah, we're going to be 5 days a week back in the office for people by the end of 2023. And then we can kind of see how we do. Another cool thing about this approach is, and these predictions and our observations are available for anybody in our agency to go and look at. What you see here is this dark line is our observed data. The dashed lines are what we predicted back in December of 2021. And so you can see is that we had a huge crash in January and February. That was Omicron showing up in Minnesota. It really did shut down people's travel, and we lost a ton of operators to being out. This spring, we bounced back, and we're kind of right in the thick of where we thought we would be when we predicted this last fall. And so we'll see what the rest of the summer has in store, but this is essentially what we can do when we're talking about ridership forecasting is give options, give scenarios, and then, it's up to the finance department to decide what they're going to do in terms of making a budget, which of course is just as much of a challenge. So, okay, I want to stop there. Thanks for bearing with all those examples, and thanks to Brendan and Amer for having me today.
Thanks, Eric. That was very cool. We'll take a few quick questions. We may run a little bit later with Catherine. With the cuts that you talked about that are affecting marginalized communities, did you consider replacing fixed route with ODT, with on-demand transit?
Yes, so we we are actually piloting, starting this fall, our first microtransit on-demand transit option. So we've partnered with a software vendor, and we have a contracted bus operator who's going to do the vehicles. And it's in a section of North Minneapolis, which would be considered historically underserved, high density of Black population. We are going to complement our existing fixed route with this on-demand transit as both a feeder and a point-to-point system. And this is a pilot. We're going to see how it goes. Really the cut trips thing is that the operations has a set of rules, the control center, about how they prioritize cuts, and the rules make sense. They try to avoid cutting very infrequent routes if it's the only trip that hour, and they try to avoid cutting the last trip of the day that's on a certain branch, and so on. So all these things make sense, but what it adds up to is they end up concentrating the cuts on the frequent network, where that frequent network serves these BIPOP populations the most.
Yeah.
So it's a balance of, okay, we know we have to serve everybody, but from an equity perspective, we have to recognize that we're potentially having disproportionate harm when we're focusing these cuts on a high frequency network.
Yeah. Does the forecasting model, I guess it's the last one, the demand forecasting model, respond to changes in supply and demand beyond the scenario analysis, the trends and so forth?
Yeah, so we have, I'd say we have a different approach we use to incorporate those kinds of changes. This is purely trend based on forecasting. We have a spatial model where we use population density and job density, important things like the number of people that are renters rather than owners of their home, students, whether there's a university, all these types of things to kind of predict the transit demand in a spatial way, and be able to roll that up to understand what our kind of ultimate ridership expectation should be, kind of a propensity mapping, if you will. And that's used more to understand, I guess, the spatial geography of where we should be doubling down on transit or investing more in transit. Yeah. We don't have a sort of mechanistic behavioral model based on population or telework, which I'd love to have, or anything like that.
Just one last quick thing from me. I was very interested in that dividing up or analyzing the trips per ethnic group. But I guess that's a lot of it is because, as you said, those marginalized groups are primarily downtown, and that's where the concentration of the services. It all makes sense. We've had a lot of discussion up here about the suburbanization of poverty, where because of this, and I know you've been investing in new LRT lines and BRT lines, maybe not less with the BRTs, but the LRT lines probably do over time push people out to the suburbs where it's cheaper. Have you observed that, or is it showing up yet, or not?
Yeah, we expect that. We haven't seen a lot of it per se. There are certain neighborhoods, I guess, which might be experiencing gentrification. There hasn't been an enormous amount of displacement from the central cities, but I think we do expect that's something we'll see. I know we were following, kind of what's studies pre-COVID out in Portland about this issue, and how that was one of the contributing factors to kind of a longer term ridership decline. Was kind of a replacement of daily riders in the urban core with people who were less frequent riders, and that all had to do with who could afford to live there. So we're definitely watching that, but it's not a main driver of things in our region yet.
Good. Okay, thank you very much, Eric. That was great.